Welcome to this lecture series on reinforcement learning and the brain. And in this video, I will make a strong statement. Dopamine as a third factor is a TD-like signal. We have seen that three factors are needed for synaptic changes. A presynaptic factor, that could be spikes of the presynaptic neuron. A postsynaptic factor, that could be spikes of the postsynaptic neuron or increased voltage. And then a third factor, which could be a neuromodulator such as dopamine. The logic is that presynaptic and postsynaptic factor together select the synapse. So a small subset of synapses becomes eligible for the change. And then the third factor is a nearly global signal, a broadcast signal, potentially received by all synapses. And then the synapses need all three factors for the change. So in the end, it's only the selected synapses that will actually undergo the change. Now, a broadcast signal could be dopamine. It's generated in a nucleus deep down in the brain, and then it ramifies out across many different brain areas. And it signals reward minus expected reward. In that sense, it is a success signal. And this is a very famous and influential line of work of Wolfram Schultz and colleagues. And here is the basic experiment that was influential for many fields of research. It's a condition experiment. Here a food reward, think of a little peanut, is given to the animal. And indeed, dopamine neurons, this is a set of neurons in the first trial. This is maybe trial number 50. So these dopamine neurons respond with high activity to the reward. Now, the animal then learns that a red light predicts this stimulus. The stimulus is called conditioning stimulus, CS. And then after 2-3 days of exposure to this situation, maybe 10,000 trials, the animal has learned to expect the reward after the red light. And we now see that the same dopamine neurons that previously responded to the reward now respond to the red light, to the conditioning stimulus. Interestingly, they no longer respond to the reward. And this is an indication that dopamine neurons are not simply signaling a reward, but they signal something like reward minus expected reward. And then we can play a trick, and after the animal has learned to expect the reward, for a few trials the reward is not given, and then there's even less activity in the neurons than they would have normally. So reward minus expected reward. Now, how can we explain the peak here? Well, remember that a TD arrow has a reward component, but there's no reward here. But then it also has value components. And the red light in my schematic explanation represents a state S prime that was not expected. It's not controlled by the animal. Suddenly the red light goes on. But the animal has learned that this state S prime is related to a value. And so even though the actual reward is 0, there's a positive dopamine signal. So we can say dopamine acts as the third factor, and it represents something like the TD delta arrow. So dopamine signals reward minus expected reward. Dopamine signals an event that predicts a reward, and we can interpret this as an approximation of the TD arrow. Let's go back to the advantage actor critic. Let's go back to a formal neural network. So we need, if we want to send a TD signal, we need a value unit. Means somewhere in the brain there must also be value related neurons. And out of these value neurons, you have to calculate this difference over 2 time steps, and you have to combine it with the reward. So 3-factor rules. Pre- and postsynaptic factor together select the synapse. Subset becomes eligible. The 3rd factor is potentially received by all synapses. And the 3rd factor, and that's what's shown by this experiment, can be the dopamine-like TD signal. For that, we need an actor-critic architecture because we need critic neurons to calculate this difference. And then the dopamine signal would be just this. So dopamine is a brain internal broadcast signal. It's not the reward. It's more like an intrinsic reward system. The first chocolate in your life tastes good and is learned to be a reward. And later just the sight of chocolate might trigger this intrinsic reward system. So extrinsic rewards are chocolate, sweet food, some drugs, for humans also praise and money. And this is transformed into intrinsic reward signal. Dopamine is generated by the brain. Dopamine is mainly reward related, but it could also contain a little bit of surprise or novelty. In any case, it's not just reward. It's really reward minus expected reward. And so even in the absence of an external reward, if you find the indication that predicts the reward will come up, dopamine will go on. And therefore, it's not surprising that dopamine is involved in drug addiction. Now, games and social networks try to make participants, to make users addicted by stimulating the intrinsic reward systems, by appropriate setup of the games or of the social network. And if you know that that dopamine is reward minus expected reward, you can decrease the expected reward for some time and then return to the normal reward back. And this will again give a new dopamine signal, a new pleasureless signal, and people will try to continue. You can talk about bonus points, about reaching the next level, and each time sort of you have the feeling, yes, I made it, it's good, it stimulates your internal dopamine signal. And I would like to criticize the setup of many social networks and computer games because they really exploit the intrinsic reward system of the brain that was set up by evolution to learn useful stuff, and now it's used to learn stuff to spend time with stuff that's not necessarily useful. So what we have seen is there's a relation between reinforcement learning rules and the brain. 3-factor rules can be implemented by the brain. The synaptic changes need a presynaptic factor, a postsynaptic factor, and a 3rd factor, and a 3rd factor could be the neuromodulator. Actor-critic and other policy gradient methods give rise to very similar 3-factor rules. So the idea is that eligibility traces are candidate parameter updates. Eligibility traces are set by the joint activation of pre- and postsynaptic factors that decay over time, but they are transformed into a weight change if the 3rd factor comes, and the 3rd factor could be dopamine. Now, importantly, the dopamine signal has the signature of a TD error, which means it responds to reward minus expected reward, and importantly, to unexpected events that predict reward. There's a large literature on the relation of neuroscience and the brain. A lot of it is reviewed in the excellent book of Sutton and Bartow, and then in addition I give you a little bit of background reading in the additional references.